But numerical people being what they are, they wanted to improve it. Like, is there a way to make it faster? And turned out there is. It turned out that the better way, basically the same idea, but just, you're always looking for a simple change. And the idea of introducing a shift was tried and turned out to work extremely well. So that's the improvement. So we take A1. No. So how does the shift work? So instead of A0, have I got space here to do this? Instead of A0, I take A0 minus a shift. So a shift is some multiple of the identity. If I just move a matrix by a multiple of the identity, what happens to its eigenvectors? What happens to its eigenvalues? Something pretty simple, right? Because I'm just shifting by SI. What happens to its eigenvectors? They're the same. And what happens to the eigenvalues? They change by S. If A naught V equals lambda V, then when I multiply this by V, there will be an extra, it'll be lambda minus S, because the identity times the V is just V. So it just shifts all the eigenvalues by S. And you try to shift, you look for a shift. This would be great if you knew lambda n. A shift there, you would be looking for 0 then, if you shifted them all by that lambda. And it turns out that would speed things up. So you work instead with this matrix as, now, again, I'm factoring it in the Q naught, R naught. So that's the work of the method, is in doing Gram-Schmidt at every step. And then there's a little work in reversing the order. And then I want to undo the shift. So I do that factorization. Now let's see. You may have to help me to remember what I should do here. So I factor those. I reverse those. And then I think I add back the shift. And that's my A1. So I took A naught, I shifted it, I worked with it, QR, reversed the order, RQ, added back the shift to get a matrix. And what am I, of course, hoping about the matrix A1 and A naught? I'm hoping they're still similar. I'm hoping, so I did a shift and I undid a shift. But of course, after doing a QR, I have to check, are these really still similar? So let me just try to check that one again. Maybe I'll just, it's sitting right there, so let me do it again. I'm hoping that something, where did we change? Oh yeah, here. We showed that A1 was similar to A naught, and I'm hoping that's probably still true, even, the shift didn't mess that up. Let's just try. So A naught, that's R naught, Q naught, plus SI. Okay. And now what am I going to do? What did I do before? I figured out what Q naught was from this. You remember? So this is R naught. Now I have to put in Q naught, but Q naught is this thing inverse times this. Is this going to work? I'm like hoping, but I don't think I wanted to get that. No, it's not Q naught there. What do I put here? And if it doesn't work, we'll leave it as an exercise. Okay. So, yeah, because I didn't sort of start right somehow. Okay. So, but let me just push along to see what happens. So I'm plugging in for Q naught here. I'm plugging in this matrix, so it shouldn't have inverted it, times R naught inverse. Who knows? It might work. Who knows? So that's the R naught Q naught, right? Is everybody with me? Sorry about this. R naught inverse. And then I have to add SI. So what have I done? I've just like pushed on, believing that this would work, because it's the method that is constantly used. Now, what do I have there? Is it working? This is R naught A, that was of course A naught, R naught, A naught, R naught inverse, R naught, A naught, R naught inverse, good. Minus S, what have I got there? From the R naught minus SI, R naught, what is that? That's minus SI. Hi, look, success. The R naught cancels the R naught inverse, so that term from that is minus SI, cancels plus SI, I'm finished. And lo and behold, we have the same similarity. So we messed around by a multiple of the identity, and it didn't, it actually makes the thing converge faster if we choose the shifts well, and but basically the same idea is still working. Okay, so that's the QR method. Well, that's the method we haven't shown and won't show, that except for this half completed example, I don't plan to prove that the lower triangular part begins to disappear, gets smaller and smaller and smaller, and then the eigenvalues pop up on the diagonal. It's amazing. Amazing. Okay. Now, is there any other improvement we can make? So that's the method. And where's the work in using that method? Because that's what we always focus on. Where are we spending computer time? Well, we're spending computer time in doing the factorization. So it didn't cost anything to shift by the identity, but then we had to factor that into Q naught R naught. Then it didn't cost much to multiply them in the opposite order. So the work was in QR. So could we think of anything to improve that aspect? Could we think of anything there? And then we've got a really first-class method. Well, if the matrix A naught, the matrix we started with, had some zeros that allowed us to skip steps in doing the QR factorization. So what am I going to say? I'm going to say if A, or A naught, our original matrix, has a bunch of zeros. Let's say it's got a whole lot of zeros there. Maybe it's well, okay, I overdid it here. I know the eigenvalues right off. But so the truth is, I can't, saying that if that, it's not going to happen. But we can get zeros with one extra diagonal. That turns out, so that here's the main diagonal. Everybody's got his eye on the main diagonal, and one diagonal if I can get a lot of zeros, but I can't by simple computations, and I'll show you how to get one. But I can't get all those to be 0, because then I would have the eigenvalues right there. And that, well, how do I know that I can't? You know, in elimination, ordinary solving AX equal B, you really do get to an upper triangular form, right? Some operator, some elimination steps you plug away, and your matrix becomes upper triangular U, and you're golden. But that's too much to expect here. In fact, we know we can't do it by simple steps, because if we could do it, if we could get to a U with a whole lower triangular part 0, we would have found the eigenvalues. And we know that the eigenvalues solve an equation of nth degree, and we know somebody proved a century or more ago that you can't solve an nth degree equation by simple little steps, right? Do you know who that was, and that you know that fact, and what degree does it apply to? So that's an important fact that you sort of pick up in math. Yeah, what do you? Fifth degree, yeah. So 5 by 5 and up would be, this is impossible. Impossible. There's no formula to find a simple formula for the